Hello everyone, this is Nash. It's now summer vacation, so recently I'm thinking about sharing an interesting topic about the Heisenberg uncertainty principle and the single-slit diffraction experiment. Actually, for single-slit diffraction pattern, we learned it before when we were a high school student. And for Heisenberg uncertainty principle, that is what you're going to learn if you're a college student with some science background or engineering background. Almost every student with science background will learn the fundamentals of physics. Actually, I can relate the two of them. We can use the single-slit diffraction experiment to help you better understand the Heisenberg uncertainty principle. And how to do that, check it out. First, we prepare a slit. If you shine a laser beam, and a laser beam try to pass through the slit, and if the slit is big enough, and you will see the spherical pattern on your screen. So even though you're not a physics student or any scientific background, let me just ask you one question. What if I now shorten the width of the slit? If I try to shorten the width of the slit, then the pattern for your spherical pattern is going to be even narrower. If I try to keep decreasing the slit, you keep decreasing it narrower. Tends to be narrower and narrower and even narrower. You start to cut the edge of the pattern. So at the beginning, it might look a spherical shape, but if you try to shorten the width of your slit, if this is the width of your slit at the beginning, if the slit is so wide, so the whole laser beam can pass through it, this is your laser pattern. But when you try to shorten the slit, the width of the slit is going to be even narrower, and you start to cut the edge of the pattern, right? You start to cut the edge of the pattern like this. You start to cut the edge of the pattern. And if you keep decreasing it, as you expect, I will see an even narrower pattern. But something interesting just happened right here. If you keep decreasing the width of your slit, it tends to be even narrower, and narrower. And something interesting just happened. When your slit is now even much more narrower, then the pattern no longer tends to be even narrower. It tends to be even wider like this. If you keep decreasing the slit, and it's so much narrower compared with the original size, then your pattern is going to be even wider. This is really non-intuitive. At the beginning, you try to decrease the slit, you try to decrease the width of your slit, and you cut the edge of your pattern. And it tends to be narrower, and so as your pattern. Even for students without any scientific background, they will have such intuitive thoughts. The narrower the slit is, and the narrower your pattern is going to be. But somehow, if your slit is not getting too much narrow, and your pattern no longer tends to be narrow anymore, somehow it tends to be even wider. So your slit is going to be even narrower, and your pattern is going to be wider and wider. That's really non-intuitive. But that's the way the world works. So if you're a high school student, you would say, hey, Nash, it's not that hard to explain. We can use the Heisenberg principle. And the Heisenberg principle tells you that every single point on a wavefront, it can be regarded as a brand new light source or brand new wave source. And it's going to propagate the spherical wave by itself. And so much spherical wave is going to superpose all together and construct a brand new wave. So that's why we see diffraction. That's why we see an even wider pattern. Okay, that's what you learned when you were a high school student. And 1 year later or 2 years later, when you're a college student, you start to learn something about the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle tells you that the delta x, that is the uncertainty in position, and times delta p, the uncertainty in momentum, should be greater than h bar divided by 2. Or you can say it's simply h divided by 4 pi. So based on the principle, if we start to know too much about the position, if we start to know the information about the position, and we know specific information about, we know much about the tangent position. We know too much about the particle's position, and that means the less we know about is velocity times mass, but the less we know about is momentum. So the more you know about the position of a particle, the less you know about its momentum. That is what Heisenberg Consortium principle tells you. So if we check this pattern with another aspect like this, this is your single slit, and this is your diffraction pattern, and this is the intensity as a function with the y-axis. All right. Originally, if you shine a laser beam, or it doesn't have to be a laser beam, it could be electron beam, try to pass through it, you expect your particle is going to travel along the horizontal direction and hit the screen. You thought that there's only one direction for the passing through particle. But however, you will see a diffraction pattern, right? Let's check the first deconstructive interference pattern right here. Deconstructive interference. First deconstructive interference pattern. Okay, you can imagine this delta P. You can imagine this, the size of the slit is the delta X. So if you try to get your slit even narrower, that means you are decreasing the delta X. Because this is the only way that the particles can ever pass through. If we got really tiny space for the particle to pass through, that means we know so much about the position of the particle. We are decreasing the uncertainty in position. So meanwhile, if you are decreasing the uncertainty in position, that means you are creating, you're even more confused about the momentum. That means that even a larger uncertainty in momentum is going to be. So originally, you should hit the wall with a horizontal direction, but then since you are decreasing the delta X, and that means you are enhancing the delta P. You're enhancing the delta P. So it could be possibly hit on other places like this. And this is your original momentum like P. Original momentum like P. But now, since you are decreasing the delta X, and more delta P is going to be occurred, and this is your delta P. It is because of the delta P, and that will change the direction of the particle. The more we know about the delta X, the delta X is not decreasing. The less we know about the momentum, and the delta P is going to be increasing. This is real non-intuitive, right? So as me, it's real non-intuitive, but that's the way the world works. So we can calculate the delta P. We can calculate the delta P and delta X. Let's check what are those results. First, if we talk about the first deconstructive interference, pattern, then the condition is the delta X times sine theta, which is the path difference. Should be equal to 1 lambda. Why? Check this. If I enlarge this part, I want to derive the first deconstructive interference pattern. Since the slit in real world, the size of the slit is really small. So if I shine two light, the two light can be regarded as two parallel lights, and the path difference is right here. This is your path difference. Your path difference, delta X times sine theta. This is your delta X, and this is your diffraction angle, and the diffraction angle right here. This is what we learned in high school physics. So this is your path difference, the delta X and times sine theta. If I want to derive the first deconstructive interference, and the condition is 1 lambda. And since the theta is really small, if it is really small, the sine and tangent and theta, they are equal to each other. So I can say the delta X is now equal to lambda divided by theta, right? So this is the first. Secondly, I can talk about the change in momentum. The change in momentum, because you are decreasing the delta x and more delta p is going to be occurred, and it is because of the delta p, so it doesn't need to hit the middle of the screen. It can hit the other positions. So many options could happen due to the delta p. So the delta p, according to the diagram, it can be expressed by p times, you can say p times tangent or sine or even theta. Once when the theta is really small, the sine and tangent are equal to each other. They are nearly equal to each other and even equal to this theta. So the delta p can be written as p times theta. Okay, now we got two quantities, the uncertainty in position and the uncertainty in momentum, and the delta x times delta p. The delta x is lambda divided by theta is lambda. Now rearrange it. The delta x is now the lambda divided by sine theta. And just like I say, when the theta is really small, sine is equal to tangent and it is also equal to theta. So the delta x can be now expressed like the lambda divided by theta and times delta p. And delta p is p theta, right? P theta. P is the h is the Planck's constant. The Planck's constant divided by lambda and times theta. Awesome. So you can now cancel something like the theta, the beta, the lambda, and the lambda. So the uncertainty in position times the uncertainty in momentum is now equal to the Planck's constant. This is what you are familiar with when you are first grade in college. So this is really non-intuitive, and that means if you're decreasing the slit, decreasing the width of your slit, that means you start to know too much about the information of position, because the slit is the only way, the only path that your particle can have to pass through for photons or for the electrons. So if you're trying to decrease the slit and you are decreasing the delta x, we know more about the position. The more we know about the position and the less we know about the momentum. So it is because of the momentum, the uncertainty and momentum. So the passing through particle cannot just hit the middle of the screen. It can hit here, there, and there, all possible. There are so many optional choices, optional directions. This is the Heisenberg uncertainty principle. All right, so today in this video, I'm just simply showing you how to use the single-slit diffraction to have a better understand the Heisenberg uncertainty principle. If you have learned the Heisenberg uncertainty principle, then maybe you can review something about the single-slit diffraction in your high school life. It cannot just simply be explained by Heisenberg's principle that every single point on the wavefront can be regarded as a new light source, new wave source. Other than that, it can be also explained by quantum mechanics, like Heisenberg uncertainty principle. Here's the thing: some people say at the beginning, we are so curious about quantum mechanics. We know nothing about it. We have so many questions. So you tend to go to study more, you go to read more in textbooks, you join conferences, you listen to speeches. But however, the more you understand, the more you read, you're even more confused. You get even more questions to ask. So if you get some feeling like this, then maybe I should say congratulations. Maybe you are now in the field of quantum mechanics. Thanks for watching, and this is Nash.